Image 1 shows the complete RO system. Feed water enters from the left side after earlier pretreatment, such as filtration and activated carbon. Even at this point, the water may still contain dissolved salts, silica, organics, bacteria, and minerals. The high-pressure pump drives that water into the RO membrane modules. These long cylindrical pressure vessels contain semi-permeable membranes that separate clean water from dissolved contaminants. The clean stream is called Permeate, and it moves toward deionization and eventually the PM electrolyzer. The rejected stream is called Concentrate, and it carries salts and impurities away from the system. This image is important because it shows that RO is not a simple filter. It is a pressure-driven molecular separation system that protects the entire hydrogen production chain. Image 2 shows why normal water fails. This is the system stress image. Untreated water may look harmless, but inside a hydrogen-grade water system, it can be destructive. Chlorine can attack catalysts and membranes. Silica can build hard deposits on membrane surfaces. Calcium and magnesium can form scale. Organics and bacteria can create biofouling. Heavy metals can poison sensitive components. In the center of the image, the damaged RO membrane represents what happens when these impurities are not controlled. Flow drops, pressure rises, energy consumption increases, maintenance becomes more frequent. Downstream, the PM electrolyzer can suffer from catalyst poisoning, membrane degradation, lower efficiency, and higher failure risk. This is why water quality is not a small detail. It is a survival condition for the hydrogen system. Image 3 takes us inside the RO membrane. This is where the science becomes visible. The membrane acts as a semi-permeable barrier. Water molecules are small enough to pass through, but salts, silica, bacteria, organics, and heavy metals are rejected. The visual shows feed water entering on one side, pure water passing through the membrane, and contaminants being flushed away through the concentrate stream. This is not ordinary mechanical filtration. In a normal screen filter, particles are blocked because they are physically too large. In reverse osmosis, separation happens at the molecular level. Pressure forces water across the membrane while dissolved contaminants remain behind. That is why RO can remove a very high percentage of dissolved salts and impurities before the water moves toward electrolyzer-grade polishing. Image 4 focuses on the high-pressure pump system. This pump is the heartbeat of reverse osmosis. RO does not work unless pressure is applied. Natural osmosis wants water to move in one direction, but reverse osmosis forces it in the opposite direction by applying pressure. In industrial systems, this pressure may reach tens of bar depending on water quality and system design. The pump must provide stable flow, reliable pressure, and continuous operation. If pressure is too low, separation becomes weak and water quality suffers. If pressure is too high, energy consumption increases and membranes may experience stress. This is where engineering economics enter the story. Every extra unit of pressure costs energy, but insufficient pressure risks poor purity. The RO pump is therefore not just a mechanical device. It is a control point for performance, reliability, and operating cost. Image 5 explains permeate versus concentrate. This is one of the clearest ways to understand reverse osmosis. On one side, the system produces permeate, the clean water stream with low dissolved solids. This is the useful stream that moves forward toward deionization, storage, and electrolysis. On the other side, the system produces concentrate, the reject stream carrying salts, minerals, silica, organics, bacteria, and other impurities. This separation is the core value of RO. The system continuously decides what can move forward and what must be removed. For hydrogen production, this matters because the electrolyzer should not receive water loaded with contaminants. The more stable and clean the permeate stream is, the better the downstream electrolyzer can perform. Image 6 shows membrane fouling and scaling. This is one of the biggest hidden enemies of RO performance. Over time, impurities can build up on the membrane surface. Biofouling occurs when bacteria and organic matter form biological layers. Organic fouling occurs when natural organic compounds clog the membrane. Inorganic scaling happens when minerals like calcium carbonate or silica deposit on the surface. Particulate fouling occurs when fine particles block flow channels. As fouling grows, the system must work harder to push water through the membrane. That means higher pressure, higher energy demand, lower water production, more cleaning, more downtime, and shorter membrane life. This image is important because it reveals that RO performance is not fixed. It degrades if the system is not properly protected, monitored, and maintained. Image 7 shows RO delivering ultra-pure water toward electrolysis. At this stage, the water has passed through the molecular separation process and is now much cleaner than normal feed water. It may still go through final polishing, such as deionization or EDI, but RO has already removed the bulk of the dissolved salts, silica, organics, and contaminants. The visual connects the RO system, the pure water tank, and the electrolyzer. This connection is critical. The electrolyzer depends on stable water quality to protect membranes, reduce scaling, maintain efficiency, and produce reliable hydrogen. Poor water quality can increase resistance, damage catalysts, shorten stack life, and raise operating costs. Clean water is not just an input. It is part of the electrochemical performance of the plant. Image 8 brings the full system together. Raw water enters the RO system. Impurities are removed. Pure water is stored and delivered. The electrolyzer receives high-quality water. Hydrogen exits the system. This image is the payoff because it shows the full chain working as one integrated industrial platform. The lesson is simple but powerful. Green hydrogen is not created by one machine. It is created by a system of systems. Reverse osmosis protects the water quality protects the electrolyzer. The electrolyzer produces hydrogen, and the entire system depends on every hidden layer doing its job. This is the deeper reality behind hydrogen infrastructure. The future hydrogen economy will not be built only by installing more electrolyzers. It will be built by understanding the systems that keep those electrolyzers alive. Water purification, pressure control, membrane protection, contaminant removal, monitoring, maintenance, and reliability all matter. If any one of these hidden systems fails, the visible hydrogen technology becomes weaker, more expensive, and less bankable. So, when we look at reverse osmosis, we are not just looking at a water treatment machine. We are looking at one of the invisible foundations of green hydrogen. It is the system that turns ordinary water into processed water. It is the system that separates what the electrolyzer needs from what would destroy it. It is the system that quietly protects performance before hydrogen production ever begins. And that is why the future of hydrogen is not just about electricity, stacks, or production targets. It is about hidden infrastructure. It is about the industrial systems behind the headline technology. It is about whether every layer can survive real operating conditions. Because in green hydrogen, clean water in means reliable hydrogen out.